Hi everyone. So today I'm going to tell you how to build a small neural network to memorize data. This is after a joint work that appeared on arXiv a couple of weeks ago with Ronen Eldar, Yin Tatley, and Dan Mikkelinser. But what I'm going to tell you about here is more of the background to this paper, which is included in the first few pages of the paper. We don't claim any novelty with respect to that material, but it's just a more unified version of what has appeared before. So that's what I'm going to explain to you today. Okay, so we're going to talk about one hidden layer neural network. So let me explain what these are. So first we fix psi, which is going to be the nonlinearity that we use in our neural network. So that's just a map from the real line to the real line. And then we're going to consider one hidden layer neural network. So one hidden layer neural networks, which are function of the following form. So I'm going to introduce some notation as I explain it. So it takes as input a point x in Rd, in d-dimensional space. And what it's going to do is that it's going to apply a bunch of affine maps. So k affine maps, exactly. So these are going to correspond to k different neurons. But let's say the k neuron, what it's going to do is that it's going to take a vector wk. So this is a vector in Rd. It's going to apply the linear function wk.x, and then it adds some offset b, bk. So this is the affine map that is being computed by the case neuron, and then it makes this affine map go through the nonlinearity psi. So what the case neuron compute really is psi of wk.x minus bk. Okay, and you have k of those. So let's say on this first neuron you have w1, b1, etc. up to wk bk. Now, this is what the hidden layer is doing with the k different neurons. And then there is a recombination of those neurons, which is just going to be a real reweighting of those different neurons, and then we sum them. So we're going to have real numbers a1 r up to ak. And the function that is being computed at the end of the day is the sum for L equals 1 to k of the output of the else neuron. So the output of the else neuron is psi L dot x minus BL. And then it's weighted by AL, and all of those numbers are recombined just linearly. Okay, so this is what we call a one hidden layer neural network. And I'm going to denote by fk of psi. This is a set of functions that can be represented like this. Okay, so this is a set of functions that can be represented as a one hidden layer with k hidden neurons and the nonlinearity psi. And the question that we're going to be interested in is how many neurons do you need to memorize? So how large should be k so that for any data set, so for any pair of points xi, yi in Rd cross R, I is going to go from 1 to n. So I have n data points. Sorry, okay, never mind. I have n data points. What happens here? I have n data points in d-dimensional space. And what I'm trying to ask is, does there exist a function f in fk psi, so a neural network with k neuron, such that f of xi is equal to yi for any I? Okay, so you perfectly fit those n data points. You completely memorize them. So this is the question we want to ask. So first of all, why is there a good answer to this? I mean, why is it that it is at all possible to find a finite k so that you can memorize your data? So notice that the universality of neural network tells you that k equals infinity is always enough. So this is a theorem that goes back to Sibenko, 1989. So the precise version that I'm going to tell you now is actually from a follow-up from Leshno et al. From 93, but this doesn't matter too much. And also, I'm not going to be too careful with respect to citations in this presentation. You can find all the proper citations in the paper. And again, we don't claim any novelty with respect to the material presented here today. So the theorem is that for any psi which is not a polynomial, for any psi which is not a polynomial. So if you take a nonlinearity which is not a polynomial, k equals plus infinity is enough. Okay, if you have a large enough neural network, then you can fit anything. Now, a very easy consequence of this is that, in fact, k equals n is always enough. So you can always find a finite size neural network that will perfectly memorize your data. So here is the proposition that we prove in our paper. Other people noticed it before. We have a very simple linear algebraic proof. So if k equals infinity is enough, then so is k equals n. So let's do the proof of this. So let me introduce a linear operator V, which is going to go from the set of neural network with, let's say, infinitely many neurons to Rn. And what this map does is that it takes a neural network and it just evaluates it on our data set x1 through xn. Okay, so I have a data set which is fixed, x1 through xn, and I just evaluate it like this. So by assumption, we know that the image of V is all of Rn. Okay, because the assumption of our theorem is that k equals infinity is enough. And for instance, by Sibenko, we know that this is true as soon as psi is not a polynomial. But what is V really? What is the image of V? Well, the image of V by definition is V of f infinity of psi. Right? That's the definition of the image of V. But what is f infinity of psi? F infinity of psi, it is in fact a vector space, because if you have two neural networks, you can add them, and that still is a neural network with k neurons, with some number of neurons. And in particular, by definition, those neural networks you see here, they are just obtained by linear combination of single neurons. So really, f infinity of psi is nothing but the span of all single neurons. So this is V of the span of single neurons. Now V, my operator V, is a linear operator. So V of the span of something is nothing but the span of V of this something. So this is the span of V of a single neuron. Okay, so you take all possible single neuron, you apply V, meaning you look at their image on your dataset x1 through xn, and you take the span of all of that, and that, in fact, is equal to Rn by definition. But so this means that this thing is of dimension n. So in fact, I can extract a basis of n vectors. So there exist n single neurons such that the span of those n single neurons through V will span all of Rn, meaning that I can memorize any value on my data x1 through xn. Okay, so this shows that you can always, if you can do it with infinitely many neurons, then you can also do it with just n neurons. K equals n, the number of data. Okay, very good. So this was a simple proof, extremely general. We basically assume nothing. But what's nice is that this is not the end of the story. So there is a high dimensional phenomenon lurking. So here is a high dimensional phenomenon, high dim phenomenon. In fact, k of order n over d is already. So by parameter counting, you should expect that this is what's going to be enough, because you see each neuron, it has d parameters, exactly, I guess, d plus 2 parameters, one more for the offset and one more for the recombination weight. So d plus 2 parameters. So in total, the number of parameters in my network is of order k times d. And we expect that if the number of parameters is larger than the number of data points, we should be able to fit. Okay, so what we expect from this heuristic is that k times d larger than n is enough. Of course, For this, we will need some assumption on the data, because it could be that all the data lies on a line, for instance. All the xi's, they just are on a line. Maybe only the first coordinate is non-zero and all the other coordinates are zero, in which case there is no really high dimensionality, and you cannot hope to exploit the high dimensionality of the data. So you will need some assumption in order to prove that this k larger than n over d is enough, which was not the case for our very general theorem that k equals n is already enough. And what we're going to assume is the simplest thing that we can possibly assume, namely that the data is in general position. Okay, which means that if you take a hyperplane, you can find a hyperplane is never going to contain more than d data points. Okay, there is no linear combination between the data points that couldn't exist by just general principle. And if we assume that, then we'll show that k larger than n over d is enough. And in fact, this was already proven some 30 years ago, so by Eric Baum in 1988. And he proved the following. For general position xi's, for binary target yi, position xi, for binary target yi, with psi of t, which is a step function, so the indicator that t is non-negative. So here we're using a specific nonlinearity. Okay, so just this is a nonlinearity, is a step function. Okay. It turns out that for general position xi, binary target yi with the step function, we can prove that k larger than 2 n over d is enough. Okay, so let's see the proof of this result. So pick d points with label 1, with label +1. Okay, and let's say for notation's sake, these d points are x1 up to xd. Okay, so we know that because it's only d points, they lie on a hyperplane. Okay, so there exists a hyperplane H that contains those d points. Let's denote it H. It's going to be the set of X such that W dot X is equal to. There is such a hyperplane that contains our d point. Now, by assumption of general position, we also know that all the other points, they are off from this hyperplane. It cannot be on the hyperplane. So let's say this is xd plus 1, etc. Maybe this is like that. Okay. So now what I claim is that using two neurons, I can create a small slice here around my hyperplane, a slice that contains no other point in my data set than x1 through xd. And using two neurons, I'm going to be able to create a function which output value 1 in the slice and 0 outside. Okay, so let's see how to do that. I claim that the following does it. Let's just take the indicator, okay, of w dot x larger than b minus delta for some small delta, minus the indicator of w dot x larger than b plus delta. Okay, so let's see what happens. So in this on the hyperplane H, w dot x is equal to b, so it's larger than b minus delta, but it's not larger than b plus delta. So I just have the one that fires, just this first neuron fires, but not the other one. So I get 1 if x is equal to xi for I less than d. Now, on the other hand, for any other data point, what happens? You see, if I'm on this side, then both neuron fires because I'm both larger than b minus delta and larger than b plus delta. So they cancel each other. 1 minus 1 equals 0. On the other hand, on this side, none of them fires, right? Because I'm both smaller than b minus delta and smaller than b plus delta in terms of my inner product with w. So any other data point, it's going to be equal to 0. If x is equal to xi and I is larger than d. Okay, so I could fit exactly my label +1 on d points using just two neurons. So I'm going to have to repeat this operation at most n over d times. And each time I add two neurons, so the total number of neurons that I have is just 2 times n over d. Okay, so this is all well and good, but there are two things that we're not particularly happy about. One of them is that this was just for binary target, whereas maybe we want to fit real values. So this, we could maybe imagine going around it by saying that we're going to feed the binary expansion of my real number, and we're going to fiddle with the epsilon. We're going to have some additional log 1 over epsilon. But it's not as clean as having something, that gives you absolutely exact fit. And also, this was with the step function, whereas in the modern practice of neural networks, aka deep learning, we like to use the ReLU nonlinearity, the positive part, the maximum between t and 0. So let's see what happens in this case. So here is the proposition that I'm going to prove to you now, is that for general position xi's, for real target yi, okay, so any real target yi, with the ReLU, with psi of t, which is the maximum between t and 0, okay, the positive part of t, aka the ReLU, the rectified linear unit. Okay, so this is just to clarify this function, right? K larger than 4 times n over d is enough. Okay, so we just have twice as many neurons as BARM network, but now we use ReLU nonlinearity and we can fit any real target. So let's see the proof of this. So the proof is based on the following very basic observation, which obviously many people have noted before. The observation is that psi prime of t, if psi is a ReLU, then the derivative is nothing but the step function. Okay, so this means that ReLU network are strictly more powerful than step function network, because you can always a neuron with 2 neurons, you can approximate the derivative by just having them close enough to each other. Okay, so certainly we already see that we're going to be able to do more than with the step function network, but in fact you can do much more in a way, because we are in high dimension and the gradient of my neuron is also going to involve a linear function. So let's see what I mean exactly. So let's say we have a neuron and we're going to do a small perturbation of that neuron. So we have W and we're going to add plus delta V for small delta inner product with X minus B. And we do this minus psi of W dot X minus B, and we divide by delta. Okay, so this formula can be computed just using two neurons. And as delta goes to 0, what do I find? I find by the chain rule I'm going to have the derivative of the inside, which is nothing but v dot x, right? Times the derivative of the psi, which is psi prime. Okay, so I get v dot x times psi prime of w dot x minus b. So you see, with two ReLU neurons, what I get is that I get the step function network neuron, but I get the step function times the linear function. Okay, so what this is going to allow me to do in my picture from before is that I have this hyperplane and I have all my other points here, right? So I can use this part, the step function, to do my indicator over here. And then I can use this part to fit a linear function here. So I can find v such that v dot xi is equal to yi. And I can find such a v because I only have d points in dimension d, and I assume that they were in general position. Okay, so the matrix whose ith row is xi, the d by d matrix is invertible. So I can find such a v that exactly solves this linear system. So to put it differently again, my ReLU network, I do a small perturbation, and what I get is I get the step function network, and the small perturbation gives me a linear function that I can fit. Okay, so to fit my endpoints, what I do is that I just replace fitting endpoints by doing n over d linear regression in dimension d. Okay. All right, but let us analyze this a little bit differently, and let us look a little bit more closely at what we did in this proof with the terminology of kernels. Okay, And this is going to be the last thing that I want to tell you about, which is memorization with NTK. Okay, so NTK stands for neural tangent kernel, and I'm going to explain this term right now. So it has been very popular in the last couple of years because we can analyze things with the NTK. So let me revisit this network that we've built here. Okay, I don't know where to start. So function computed in previous proof. So notice that in fact, by the way, for ReLU network, this limit when delta goes to 0, in fact, it's an equality for delta small enough on any finite set of points. This is because ReLU is piecewise linear. Okay, so the derivative is in fact, you don't need delta to go to 0. This is going to be true for delta small enough. Okay, but it doesn't really matter. The point is that the function computed in the previous proof is of the form sum for L equals 1 to k, and I have VL dot x times psi prime of WL dot x. And let's forget about the minus BL for now. So another way to write this is as V dot phi of x, where in V, I'm going to concatenate V1 up to Vk. And in phi, I'm going to write phi of x is going to be x times psi prime of W1 dot x up to x times psi prime of WK dot x. Okay, so this phi of x, this is a vector in dimension rd times k. Okay, you see, each neuron gives me another copy of x reweighted by psi prime of whatever was the weight vector of that neuron. Okay, wi dot x. So really, on the right-hand side here, this is a kernel method. Okay, you have an x that you embed in some higher dimensional space, and in this higher dimensional space, you're just doing a linear function. You're just doing a linear regression. Whereas, what do we have on the left-hand side? On the left-hand side, we have a neural network perturbed around the WLs. Okay, so really one way to think about it is that we have these WLs and we're doing a small perturbation, and this small perturbation gives us in fact a kernel method as a function of the small perturbation. So if we really want to talk about just a kernel method, we cannot optimize over the W's. We have to consider that the W's are fixed, they are given beforehand. This corresponds to the embedding, and the only thing we can optimize is over V. So the Baum proof that we just gave before is optimizing over both the W, the base vector, base weights W, and the perturbation V. The question of memorization with NTK is, can you memorize if now the W's you're not optimizing over them, but they are taken as at random? So you have a random initialization and you just optimize over the small perturbation. And this is useful because if it is true that you can memorize this in this NTK regime, then you can hope that something like stochastic gradient descent or some incremental method will be able to do it also. Because you see an incremental method, it will start at some initialization and just do small perturbations of it. Okay, so this NTK regime is very informative. It's very interesting. So the question is, can we memorize by optimizing only over V with W1 up to WK random, let's say random from a standard Gaussian? This is a question of memorization with NTK. Okay, and of course, the real question is, the answer is going to be yes if k is equal to infinity. The real question is, can you do it when k is of optimal size? Okay. So the theorem that we prove is that the answer is yes, with k, which is of optimal size up to a log factor. So k is of order n over d. But we will need one more assumption about the data, because if the data, if everything is very close to a low dimensional space, it's going to be very hard to do it with just random W's. So what we will need is, we'll get optimal size. So yes, with k of order n over d and xi well spread. And all that will mean is essentially, all that will mean is that xi dot xj, the inner product is much smaller than the norm, because they are not too correlated. They don't lie all on one direction, basically. Okay, which is going to be true, for instance, with random data in high dimension. I'm going to make this more precise in the proof. Okay, so this is what we're going to prove now. So how to analyze NTK? So recall, what we want is to find V such that V dot phi of xi is equal to yi. So we'll just care about a certain linear regression over those phi of xi. Okay, so let me rewrite this. This is just x transpose V equals y, where, okay, capital Y is just the vector of yi's, and capital X is a matrix whose ith column is phi of xi. So I get phi of x1 up to phi of xn. Okay, so X transpose, you see the first row is going to be phi of x1 transpose. So when I do that times V, I get phi of x1 dot V. And I want this to be equal to yi. Okay. Now let me rewrite this y. I can just rewrite it as x transpose x times x transpose x inverse times y. Okay, so if x transpose x is invertible, I can write it like this, and so this would be V. So all I need, so the goal is just to prove that x transpose x is invertible. That's all we want to prove. Okay, so that we can do the linear regression, and so we can memorize in the NTK regime. But what is this matrix X transpose X? So let's see, the ijth entry, it's the ith row of X transpose, meaning the ith column of X, times the jth column of X. So it's phi of xi dot phi of xj. So this is a matrix whose ith j entry is phi of xi dot phi of xj. Ij in N. But what is phi? Again, what is phi? Remember, phi of x is just the embedding given by the neurons. So it's x times psi prime of w1 dot x, etc., up to x times psi prime of wk dot x. Okay, so phi of xi dot phi of xj, this is nothing but the sum for L equals 1 to k. And you see, when I do the inner product, I get xi dot xj time psi prime of w L dot xi time psi prime of w L dot xj. But now we're going to have some concentration that happens, because as k becomes very large, remember the WLs are IID standard Gaussian. So this, I should expect that it will be some fluctuation around k times the expectation of xi dot xj time psi prime of w dot xi time psi prime of w dot xj when w is from a standard Gaussian. Right? I expect my matrix XX transpose to be basically equal to that plus some small perturbation. Okay, and this small fluctuation, you can control them in many different ways. This is not what we're going to focus on. So let me call this Hij. So the goal now, we can reduce the goal up to some easy to do concentration. The goal is going to be to prove that prove that H, which is, by the way, just to be clear, an n by n matrix, is far from rank deficient. So it is full rank, and it is also far from being rank deficient. Because if it's far from being rank deficient, then x transpose x, sorry, which is a small perturbation of H, is also going to be full rank, meaning invertible. So all we want to do is to prove that. Okay. Now notice that in H there is xi.xj, and there is this part of psi prime w, psi prime w.xi, psi prime w.xj. So the red part of xi.xj, this is an n by n matrix also, but it's of rank d, and n is much larger than d. So just the xi.xj part is never going to give you full rank. You have to get full rank from the green part, from the psi prime, okay, which of course makes total sense. Now, the magic is that you can write exact analytical formula for this H matrix. Namely, here is a lemma, which was proven, in fact, for completely different reason in the famous Gomans and Williamson paper on better approximation ratio for the max cut problem. But what they prove is the following. With psi equal ReLU, meaning psi prime is the step function, Hij, there is an exact formula, which is 2 over pi xi.xj times 1/4 plus the arcsine, the inverse sine function, of the angle between xi and xj. xi.xj over the norm of xi times the norm of xj. Okay, so we're not going to prove this. This has been, for instance, you can find it in my convex optimization monograph and in many, many other places. Notice that this is not a high-dimensional lemma. This is a two-dimensional lemma because all you care about is the span of xi and xj. It's just a two-dimensional computation. So you can easily do it in many, many different ways. But the point for us, so the key for us, is that arcsine of z, this is of the form, when you just do the Taylor expansion, sum from m equals 0 to infinity of some coefficient cm times zm. And all the cm's are non-negative. And in fact, the cm are strictly positive for m odd. Okay, so this, you can just calculate from the derivatives. So what this implies is that h, it's really of the form sum from m equals 0 to infinity of some cm prime, okay, the different cm, times xi.xj to the m. And let me just assume now that the norm of xi is 1. Let's assume everything is normalized so that we don't have to carry these norms around. It doesn't really matter. Okay, so this is just, I use this formula and the fact that arcsine can be written in this power series with, again, cm prime is non-negative and cm prime is strictly positive for m even. Okay, m even because notice here I have this xi.xj in front. Okay, now note a PSD, positive semi-definite, implies that in fact the Hadamard power, okay, so if I raise all the entry to the power m, remains non-negative. Okay, this is called Schur theorems. I mean, in any case, you can check it easily. So this implies that my h is larger than cm prime. Sorry. Okay, I don't know why I can't erase this. Cm prime times xi.xj to the m. And just to be clear, I don't know if this was clear. When I write this on the right hand side, it really means the matrix whose ijth entry is xi to the j, xi.xj to the m. Okay, here's the same thing, xi dot xj to the m. This is the ijth entry. Okay, this is just using this Shor product theorem. But now what does this matrix looks like? This matrix, okay, it has ones on the diagonal, and off diagonal, you see it's this xi dot xj that I assumed in the assumption of my theorem. We go back. I assume that my xi were well spread, meaning the inner product is much smaller than 1 when we normalize by the norm of xi is equal to 1. So here we have something much smaller than 1. So if this thing much smaller than 1 is really much smaller than 1, let's call it omega. So if n times omega is much smaller than 1, then in fact h is diagonally dominant. Then h is diag dominant. And in fact, it's even true if we do h minus, cm prime. Sorry, and there was a cm prime here. It's even true if we do h minus cm prime over 2 times the identity. So really, this means that h is larger than cm prime times the identity, which is exactly what we wanted. It's very far from being rank deficient. Okay, so let me just show what is this omega if we add a random point on the sphere. So just as an example, if xi random on sphere, then the inner product xi dot xj is smaller than something up to a log factor of order 1 over square root d. So really this omega is 1 over square root d. And sorry, I was, this omega is 1 over square root d to the m, right? So what we want is n times n over d to the m over 2 to be much smaller than 1. Okay, which is just n is some polynomial in d. You don't want n to be exponential in the dimension. You just want n to be polynomial in the dimension, and you're simply going to pick m to be large enough so that d to the m over 2 is larger than the number of points. And then, all the theorems, they will have some dependency on this m through this constant here. But these are all constant things. Okay, so this finishes the proof that NTK can memorize with optimal size. Now let me just make a comment about where did we use exactly the ReLU. So we use the ReLU insofar as we had this formula. Now this formula only mattered because the arcsign can be decomposed in this power series with only non-negative terms and strictly positive terms for any m large enough. Because eventually we're going to apply this with m large enough so that d to the m is larger than n. Okay, but if that's all you want, if all you want is a formula like this one, then in fact there is a much simpler way to do it. So note, with psi, which is the mth Hermite polynomial, and it doesn't really matter what it is, it's a certain polynomial of degree m. But if you take psi to be this Hermite polynomial of degree m, then you exactly have that H, the Gram matrix of the neural tangent kernel, is exactly going to be xi dot xj to the power m. And so in this case, everything is very clean and works really, really well. And m, this constant m, is just the number large enough so that d, the dimension to the power m, is larger than the number of data points that you have. And this is the entry point to the real part of our paper with Ronen, Yintat, and Dan. Namely, in addition to memorization, you would also want to have the function computed by the neural network to be fairly regular. So if you notice, the Baum network that we constructed is extremely irregular. It's like it jumps to 1 in a very thin slice, and then it's 0 everywhere else. So it's terrible in terms of generalization. A good question to ask then, we think, is can you get memorization with a network which is not that irregular? And one way to measure regularity is to compute a certain norm of the weights. And there is a very natural norm of the weights, which has appeared in many prior works, which is, for instance, called the path norm. if you follow Natis-Rebur's terminology, but it's just a very natural upper bound on the Lipschitz constant of the network. And what we show is that with Hermite polynomial, in a certain way, you can obtain optimal size network where the size is measured in terms of this norm. So this would take much longer to explain, and I'm already way over time compared to my previous videos of this format. So I'm going to conclude here. Thanks a lot.